Alright guys, today we got another video for you. We're gonna talk about CAN bus. And today, back at my side, Daniel. So, good to have you back, mate.
Good to be back.
CAN bus, controller area network. So, what do you think about this? How important is that even when we talk about hybrid and electric vehicles?
Well, absolutely critical. So, it's the main communication system that we find on a lot of vehicles now. Lots of different types of CAN bus. We hear about CAN high speed, CAN low speed, CAN high, CAN low, all of these different terms. And I think it's something you sort of need to have a little bit of experience and perhaps someone just to explain it in a little bit slower, more practical orientated version. So.
Okay, but there's one question. So when I think about the car, so you don't see it, but we have here Audi Q5. Explaining CAN bus at the car, this is like, I see it as a real challenge. So what gonna we do about explaining CAN properly?
Yeah, exactly. So it's a good point. If you have a look on a real vehicle, obviously you've probably heard about CAN bus, and that's where you've got the twisted wires. They call it the twisted pair.
Yes.
And you'll often see them in the vehicle. But obviously these are all hidden away, so under the door panels and things like that. And we actually have a door connected here. So we've got our Unitrain system, and we're going to have a look at what it looks like on this today, because it's just a little bit easier to access and to sort of see what's going on behind the scenes. But as far as using a real vehicle, there's only really one place that's easy to access without removing door panels and things like that.
Or drilling a hole inside the chassis of the car.
Yeah, and that's on the OBD plug. So having access to the CAN pins there, but you're seeing a high-speed signal there, and it's only certain messages. So it's one way to see if the system is operational. But if you look around the vehicle, there's lots of different CAN networks. So not just one CAN network. So I just mentioned at the OBD you'll have CAN high speed, and that's where the communication to the scan tool is occurring. It's over that CAN connection.
And obviously the car manufacturers give different names to this CAN networks, as diagnostic CAN, or drive CAN, for example, comfort CAN, something like that.
Exactly. There's the various, as you said, manufacturers have their own version, but essentially the principle is still the same.
Yeah.
So, and what we'll do is have a look at some of the various systems. We'll start off with the CAN low speed, have a look at CAN high speed as well. A little bit later on.
And they are running on different speeds, so this is somehow why you need a gateway. So when you are talking about network systems inside the vehicle, you always hear the word gateway, which you can understand like a train station basically, where different trains, like high-speed trains, like very comfort, slow-speed trains are coming together, and they are connected with each other, so that the data, the persons, can jump out from the one train and got into the another train. So
you can kind of think of it also like a translator. So
true,
it's changing languages of the different speeds, so that there's sort of one voice for the vehicle everywhere as well.
And it's understood by everyone basically inside the car.
If you think about the different speeds, by the way, we know this from computing, that the faster computers are, the more they cost. So that's the reason why we might have different speeds, CAN bus speeds on the vehicle.
For sure.
So CAN high speed is used for safety, for motor control. So your braking systems, your steering, your sensors, your airbags, all of those
systems,
things.
Exactly.
Exactly. They're using CAN high speed. If it's something like turning the windows up and down, then that would be a low speed CAN bus.
Absolutely. So I think you are saying, it's very thrilling now to have a look inside the CAN bus, and especially one thing where we will have the first look is at the physical signal, basically what we can measure at the CAN. What is here the problem when we go to the real car? Of course, you will not have just one message sent on the bus, but you will have like 1,000 messages of the bus. So when you connect your oscilloscope or your measurement tool to the CAN bus inside the car, the signal, what you see there, is not the result of one message, but out of 1,000 messages. And we will have a look now how it looks like when we just have one message on the bus, what we can do with our CAN bus trainer here.
Okay, so we'll have a look at this system here. This is our Unitrain system. You might have seen it in a lot of our training videos before. And we've got these cards here, which is our CAN bus course. And you can see there's 4 wires on the system right now, and the system is literally running over these 4 wires. So we have a positive and a ground, so that's obviously our power supply, and then we have our CAN high and CAN low here as well.
So speaking of 12 volt here, of course.
Exactly.
The cool thing here, we're using real CAN bus nodes here. That means I can even separate these 2 experimentals from each other, and the whole system's working. So just to show it to you that here a real CAN network is established.
Exactly. So if we're looking at the system here, we can see we've got mainly a lighting system of a vehicle. So we've got the blinkers, the indicators here, the hazard lights are operating now. If we turn the indicators left or right, see that. You can even open the doors here and see an internal light switching on as well.
So maybe a question there. So how do I have to imagine that? When we go back to older cars, basically I had a physical connection between the switch and the light bulb, for example, or whatever. So when we now have a look at CAN bus here, and of course you see what you showed us, we have physical switches here, and we press on them, and then suddenly the light goes on. But what happens inside the techniques? Is there a physical connection between the switch and the light, or how is that established in CAN bus?
Obviously that's the old school way, is having a switch going through to an actuator, which is then 1 for 1. Mm-hmm. One switch is available for 1 action. So you can imagine the mirrors on your vehicle, so going up, down, left, right. You need 4 switches and 4 cables just activate, and then the return of that as well.
That is how it was back in the day.
Exactly. You can just imagine with all of the functions that you have on a modern vehicle, how big would the cabling be? As we're seeing on the screen right now, it would just get huge.
So just here, if you have more cables, that means more weight, but also more costs. And those are the things what the car manufacturers want to avoid.
Exactly. So what we're doing here, using CAN bus. So you might have known bus, USB is also a bus system as well.
Sure, yes.
Universal serial bus. So it's a digital communication. So in other words, what we're turning now, instead of having a 12 volt on-off signal, we're now having a communication or a data communication, a digital communication occurring across essentially these 2 wires right here. So what we'll do is we'll just bring up our oscilloscope in this matter. So we have our 2-channel oscilloscope in this case. So we have channel A going to CAN high. We see CAN high written on here, but we can also see by reading the oscilloscope signal if it's CAN high or CAN low just by looking at it as well. CAN high, for example, is, I always like to say, is CAN wants to go high. So it's the one at the bottom.
That's a good thing.
Going up.
Keep that in mind.
CAN low wants to go low. So it starts off high and goes down.
So, and you have now the trigger, but when we remove the trigger, this is what you would see first. So basically what you see here, and this is basically also what you would see when you use a multimeter to measure it. You have the CAN high at 5 volt more or less, and the CAN low at 0 volt, because that is the average voltage on the channels. And just with the trigger, you are able to see the signal changes which are creating the CAN signal, okay?
And I think what's important to recognize here is we're not measuring against each other.
Yeah.
We're not measuring CAN high against CAN low, we're measuring CAN high against ground, and we're measuring CAN low against ground. And as Christian mentioned before, now in a real vehicle, you're most likely going to see something. We just seen something come up then, but if you're not very well informed about using a trigger, it could be a little bit hard to see. So if we use...
One question here, mate. So when we just have these, let's pretend that we just have a multimeter where we read these values basically. Now we have 5 volt here or 0 volt here.
Exactly.
But there's also some, because sometimes it is said like, you can't use a multimeter for CAN bus as you have to see the signal. But when we have, for example, have short circuit against ground from CAN high,
exactly,
or a short circuit against plus at ground, this is also diagnostic information where you can see, okay, here's something wrong. I don't have to go further with oscilloscope. When I see that can low, for example, is always at 5 volt, then we have there a problem, obviously.
Exactly.
Right?
So it might be a first case to see if there's anything wrong.
So you can use the multimeter for a first diagnosis if you just want to have a very principle or the fundamental diagnostic and want to get a very easy information on that if the average voltage are fine or if you even there already see a problem.
The thing you've got to realize is it comes down to diagnosis. So in other words, you've got a vehicle that's not operating correctly. The lights aren't working or a certain door is not working. A lot of cases there's also the vehicles are getting flat batteries because the CAN bus system is not going to sleep. So it's not necessarily about the signal. I haven't had many cases where the signal changes. We'll have a look at what that signal means in a second, but it's about what the signal looks like. So it doesn't really matter exactly what bits and bytes are coming through. It's about what does the signal. We can have high resistance, which causes the signal to look funny.
Yes.
So it's really about understanding what should we expect from the signal and where the problem is. So one example I had, for example, was a police vehicle, and police vehicles, they often put extra radios and things in there, and they usually just put screws straight through the body of the vehicle. And I had a vehicle like that, and they went right through the middle of the CAN bus. Short-circuited together, exactly. It was causing all these problems on the vehicle. The screw went right through the middle of the twisted.
So that means basically it connect CAN high with CAN low, and you have somehow a similar signal on both sides and not the different signal anymore.
So what that looks like, for example, here, so we've just put the trigger on. If you're not sure of what a trigger is, we can see up on here we've got a T for trigger for the time. So that's what time we want the trigger to come on, and then we've got it at a voltage level for that here as well.
If you have more questions on oscilloscope, stick to our oscilloscope video on the channel. There you find it as well, where we have a deep dive into the adjustment of oscilloscopes and how you're using it.
Exactly. It's a really good video of that. What we have on this one here, which I think is really helpful as well, is a CAN monitor. So it's one thing to see, this is called the physical layer, but also to see what the actual data is. There's a mathematical formula for all of this data that's being sent through. So what we have here is all of the messages that are being sent around on this training system right now, and I'm going to turn them off. So right now, and this is where using a trigger becomes quite handy, because you can see here we've got an out of range on our trigger. The red light is glowing and there's nothing happening on our we can see the oscilloscope is still running here, that's fine, but there's nothing occurring.
No signal. But we have to say, basically, this is impossible to create on a real car, because as soon as you open the door or something like that, you will awake the CAN bus, or even when you have a smart key system, you go close to the car will open, the CAN bus is awake, and it will communicate.
It's literally thousands of messages per second. For a couple of seconds.
What you see here is really silence. The CAN bus is not speaking to anyone else in the network. So it's basically really shut up. And now again we have the communication on the CAN bus again, as Daniel triggered the signal.
So I'm just turning the lights on and off here. And this is interesting when it comes down to learning. What is the CAN bus doing and how does it do it? So I'm just turning the lights on and off. And I think for me is what the really interesting part is, if you have a look at the signal right at the front. I like to think of this as like an envelope. You're sending an envelope, a letter to a friend.
Yeah.
You've got the envelope, you write their name and address on the front. And that's what we have at the front here, is a little bit like the identifier. That's like, who's the message for? And then you've got the message inside the envelope. And that's what we see here as well. So if you have a look closely at this signal here, the first part of this CAN bus message is the same, and then it's this section here which is changing, and that's the data. That's the basically the orders of the message.
Can we even zoom more into the signal, or?
We should be able to. So if we increase the time resolution here, So we'll do that again.
Ah, amazing.
So this is where it gets to be really interesting. What we can see is occurring there. So the first part of the message is the same, and then it changes at the back here. So what I'll do, that's the headlights on and off, and then high beam. But then if I turn the brake lights on, we can see now all of a sudden we have a different message.
Absolutely, perfect. And that's a cool, so maybe just one word for the time division. You really have to see that you choose the right time division, as, yeah, you see now you have a different view on the signal. When everything is too close, you see there is a signal, but basically you won't see what will change there. And when you dive more or zoom more into it, then you have the chance really to see what's happening there. So always make sure that you find the right time and the right voltage division for your signal, what you want to measure.
Exactly. So this is the information that's being essentially created by engineers when they design the vehicles and design these systems. And so it's not necessarily interesting for a technician. You can't change this. There's not much you can do, but you can see if there's a problem with it. But what we'll do is with this CAN monitor, where I switched on the individual systems, I can also collect the information as it's coming through. So let me just make this one a little bit bigger this time. And as we press the different buttons, so high beam, we can see how the identifier of 4 is for our headlights. And what's interesting here is 00, in this case, means off. 61 is on, 63 means high beam, that we can see here. We have brake light here, that's another identifier has just come in.
And maybe just to say here, what Daniel mentioned here, we are on the hexadecimal system. So that means when you see all the F's, A, and so on, this is because this is shown in that system, which is of course different from our normal system.
Exactly, yeah, and that's also quite interesting as well there. We can see how the hexadecimal rises up, and you might have seen that is actually correlated to the brightness of the light here.
Yeah.
So you can often see that in a lot of vehicles, how the light can adjust.
Yes.
And it's essentially
brightness level, basically.
The brightness of the level, and that's happening here. So there's for every single setting of the brightness of a lamp, there is its own CAN bus signal we're seeing here. C, 2C to...
and that's so fantastic about it. So just remember about, maybe you have seen that when a car in front of you just go on an emergency brake and suddenly the stop lights or the brake light starts to flash. This is realized through CAN bus. If you have a classical car, like an old car, old Golf or whatever, there you just push the brake. This is setting a physical connection, lights go on, nothing more. But now, because we can send all the different information and they can be taken into account from the control unit for the lights, for example, it said, I have now an emergency brake, a really hard brake, so I will change the control of the light that they do not just bright up, but that they start flashing. And this is only realizable through CAN bus.
You can imagine all of the other things as well. Like you've got a driver's key that's programmed to a certain driver. Seat goes back. All of these things,
Absolutely.
all of these functions are because of CAN bus. So we've just had a look there. We can see here, this is our CAN monitor, and we can begin. This is, some people call this CAN sniffing. If you can go through and find out which message.
Reverse engineering. Whoa.
Exactly. So what we're going to have a look at now is we're going to connect the door up to the system and just see what the difference is between the training system here, which takes it slowly, step by step, to understand what's going on, and the real door that we have here. Now, this door is actually just one door, obviously from a vehicle with 2 or 4 doors. And also it's a Golf 5. So it's not even a modern vehicle. I mean, it's it's got a few years on it, but it's still got a CAN bus system. So just take a quick look at this CAN monitor and the explosion of messages that we'll see.
Wow.
So you can see here the ID is the ID that is being used, and then here the count is the number of messages that are being sent with that just ID alone. So this is roughly about
perfect
250 messages per second. 4 seconds, you're already at 1,000 messages.
Crazy, isn't it? Wow.
So this just can sometimes be a little bit overwhelming when you're trying to learn. So what is it that you're trying to see? You know, if you just have a look at this message, and let me change that time resolution again, something a little bit slower, and all of a sudden you're looking at a very full, messy oscilloscope signal. And this is actually a very clear oscilloscope signal. On the vehicle, it often looks a little bit you know, a bit skewed.
But this is what I mean at the beginning, when you have no idea of CAN bus and you start with, and this is even compared to a real car that are just less messages, that not much. But even here, like Daniel said, it's completely confusing, isn't it? So perfect. But basically, so that we also see that we haven't simulated anything, I just want to quickly show it to you. So we really can now control the complete door. And what is funny here, we will later do a deeper dive into CAN bus, but basically now you have to calibrate from the CAN bus perspective this window. You need to get to the lowest point. This will be recognized by the CAN bus and something will change in a certain message. And then you have to go up to the highest point and also learn about the highest point, basically. Then you have sample locking, and now you see I've closed the sample locking, open it, close it. But as the system now knows basically about the position of the window, it really counts now. It exactly knows now that the window is at this certain position, and then it can say as a comfort function, when I close the vehicle, I close the window as well, so that the car is really safe and secured.
And I think what, from my perspective, gets really interesting, especially for students when they're learning about this, is how can we change from the inputs that you see within a vehicle to the outputs, the actual system, what's actually going on inside the system. So we can have a look inside the CAN monitor here, for example, and we can have a look to see which signals are changing just when I touch the button. So here the window goes down,
yeah.
Up here, B. So let's have a look at that 0, 0. That's when I'm going down. If I go up to B, 0, 8 is going up. So the next step now is let's go to send. So we have a look here and we can see now all of those. So identifier. There's another thing here called data length code. So that's how many bits and bytes that you find in the message. So this is just a basic message, so it only has the data length code of 2.
The byte packages, basically. So for each of these 2 digits, you will have, so like it said in the first row, what you see there, 0, 0, B0, 8, 0, that's 3, because you have 1, 2, 3 packages there.
Exactly. So I'm just going to replace that with a 0, 8. Christian, can you just press the enter button, press and hold it down for me, please? Change that signal to 4 and try it again. So completely just using the keyboard, and we're controlling the door.
Daniel becomes a CAN bus control unit, basically. And that's also interesting about security. The CAN bus is basically a very safe system as long as you are not a CAN node, or as long as you do not connect as a CAN node to the system itself. So that's why, yeah, sometimes when you have funny pictures on the internet where people or where thieves try to capture a car, they really sometimes try to bore a hole in the door in order to access the CAN node at the door. And when you are able to do that, that you become a CAN node, or that you can access the CAN node, then you can send signals on the CAN bus, and the car will accept them, as you've seen that here right now.
So I think we've all heard about hacking, exactly what you're talking about. The most common method of doing that, people are using the Bluetooth OBD connectors, putting that onto the OBD connector, and they're connecting via Bluetooth. So a lot of people are not always checking their OBD connector. There's quite small OBD you know, these Bluetooth dongles that you find, they're putting them on there, and so you don't notice that as a driver if it's tucked away somewhere. And then as you're driving along, they can connect via Bluetooth. So that's been the most popular method for hacking into vehicles.
And just a small excursus here, side information. This is one reason as well. It may change today as they have different bus systems at all, but back in the day, LIN bus is always used for adjusting the side mirrors, for example. Why is that so? One example or one reason is the safety behind it, or since the security reasons, because you can easily access the mirror, just remove the glass, and then you basically have access to the cables. And CAN bus doesn't have a master-slave system, so in CAN bus, each CAN node is a master basically, because there are other basics of how they are talking with each other, so that they not talking at the same time basically. So this has to be this has to be solved, the problem. At the LIN bus system, you do it with CAN master, with slave and master. And as long as you're not the master, you cannot send anything on the bus. And this is why you're using LIN at the side mirrors, for example. As the master is hidden inside the car, you cannot access it. But when you would use CAN there, you can easily get access to the CAN network from the outside.
Okay, so I think that's covered quite a bit as a bit of an introduction into CAN bus. We'll go through and have a look at a later date just some of the other things such as CAN FD. That's another system that we'll look at one day.
Just one question. What happens now when we are at low speed and when we now lose one connection?
That's a good question. So that was going to be the next thing, is go onto CAN high speed, and there's as we mentioned at the very start, CAN bus is a part of two cables. And if we just go back and have a look at the signal again, so it's quite interesting in this. And what I'm going to do is channel B, the red signal here, I'm going to invert that for a second. So invert it literally just means to change the voltage that's being represented on the oscilloscope.
Like a mirror.
Exactly. And you can see that the system, the two signals are exactly the same, just opposite. And the CAN bus signal is actually looking at the difference between these two signals. So right now it's at 5 volt and 0 volt, very close to, and it's actually trying to measure the voltage between these two. That's what it's using as its sort of signal processing. So you mentioned, Christian, if part of the signal, if we cut one of those cables, what happens? So this is low speed CAN. We can tell it's low speed CAN because it has this 5 volt difference between them. And if we press the buttons here, we can see the system actually continues to operate.
On both sides, so not just on the front node, but also on the rear node.
And you can see with the signal here that it's quite messed up a bit. So there's a little bit of signal getting around from the other side that we're picking up on the oscilloscope here. But the message of the system is working, but it's still operating. And this is a feature of CAN low speed. So it can operate in one wire mode, it's called. So if one wire gets cut, it will continue to operate. It's going slow enough for the computers, the control units to still understand what's going on and operate.
And that's why you use that, for example, at comfort systems, because they are not safety relevant, but it would be really annoying when one cable is broken and, for example, you can't use the seat adjustment anymore. So then you have much more often to go to the workshop. Even when now one cable is broken, for example, after 10 years, you still use the system from an outside perspective, like everything's completely okay, and basically there's no need to go to the workshop. Of course, you will have a DTC in the fault memory, but for the driver, you won't have basically any negative aspects there.
If we go to high speed, which we said before is often used in safety critical systems or the engine control where things have to happen instantly, we're using high speed and it doesn't have this function. So if one of the wires is broken, the system will actually shut down and warn the driver or shut the vehicle down according to what the problem is. And so with our training system here, we can simply change it now to high speed, and we can see that signal almost looks like it disappears.
Yes.
So we're lucky to have the trigger actually work still. So if we had the trigger in the wrong spot, all of a sudden we wouldn't see that signal. So if we turn it off again, you'll have as much, probably even less chance to see the high-speed signal because it's much faster, which means the same message is occurring in a much smaller time frame.
And the big difference, what you see here, so we still have CAN high and low. So don't mix that up. That has nothing to do with the speed. That are just the different channels basically at the CAN bus. So you have CAN high and CAN low at low speed, but you have also CAN high and CAN low at high speed. But what you see now, Daniel, that the average voltage of both channels has changed.
Exactly. So we can actually switch between the two now, and you can see how it's same but different. So we've got two signals. I'll switch to high speed, and now all of a sudden, now what's interesting is high speed is still trying to go higher, low speed is still trying to go low.
Yes.
So, but instead of having the difference between them, now the two are at about 2.5 volts together. So they're in the system here and they're going away from each other. And we can see here that the same message that we've seen before is now occurring in a much smaller time. So that's one message right there. And so we can even work out what the time frame is for a message. So this is 200 microseconds. So 200, 400, about 600.
Something like that, yeah.
For a message.
600, 800.
If we change it then to high speed, all of a sudden it's within 100, less than 100 microseconds.
So what does it mean? That means, just spoken pretty easily, that in a shorter time frame you can transmit the same amount of data. So what of course increasing the speed of the system.
And that's what we're saying before about the processing power to do this. Is it needs bigger processors, better processors, more expensive processors. So you don't see this. Modern vehicles, I think a lot of them have started to go to a single bus speed, so 500
something like that, yes. Yeah.
Megabits per second. Not all vehicles, obviously older vehicles have a mixture of these different speeds that you'll find on there. But this now all of a sudden is a high speed system. The blue is the high, wants to go high. Red, low speed, wants to go low. So it's really important. A lot of people don't understand. You hear CAN high, CAN low,
exactly.
CAN high speed, CAN low speed. It can be a little bit confusing.
And what will happen now when I now pull out a cable?
So let's do it. Let's see what happens.
Okay.
And what's really interesting, if we can see this from the overhead, that the front of the system is still operating. We can turn off and on the lights, but the back of the system isn't operating. Still got one wire connected, but the system is not operational.
And here also, for you to understand, from the physical signal perspective, we are measuring on the side where no interruption is. So this is why we have the full signal still. But when we would measure on the other side, now here basically where the cable is gone, you would see the difference then in the signal.
And that's where it becomes very important when it comes to measuring. So we can put that into a CAN mode there. Now it's gone. We might have to get a bit creative with our oscilloscope usage. This is where it becomes vitally important to understand how to use an oscilloscope. Understand where these CAN nodes are around the vehicle. You might have to start going to various nodes, the gateway, to see where is the message. So you've got various points where you have a nice signal, and then you have other sections where the signal is ruined. There's a short circuit, an open circuit, a high resistance, and that's the basis for doing the diagnostics on these systems.
And basically what you see here now, also that you do not wonder, or makes you wonder, the principal behavior of the CAN high speed is then that the signal or the side, the node which has lost one signal or both signals, it will stay in its last condition. Okay, that was why the blinking lights were just on. In a real car, that's a little bit different there. So basically the CAN bus would behave the same way, but the car manufacturer, they do establish different kind of limp home mode programs or emergency programs. So just in another example, when you have the high beam on and suddenly you get interrupted, when there would be used a high-speed CAN bus in that instance, for example. So it can be, so the car manufacturers can do that. So just let's pretend we have high speed for the lighting control in that case, like it is here now. And when you lose the connection then, I think it's obvious that the car cannot stay in the mode where it just leaves the high beam on. So when it detects that no information is coming again regarding the light control, then it will fall back in an emergency mode, which means for the high beam, for example, switching it off so that you don't drive all the time with the high beam.
And that's actually, also another important feature that you see in a lot of modern vehicles, it will tell you when the globes are blown. True. So on the lighting system.
Yes.
So if you'll get a message on the dash saying, hey, one of your tail lights is out, and you're like, how does it know that? So another interesting fact with CAN bus is they don't use fuses with these systems. They're able to measure the amount of current that each circuit is outputting as well. So it can either say, okay, there's too much current being drawn, we'll turn the system off.
True. Yeah.
We don't just blow the fuse. That's old school. We don't need that. Same goes for when it's sending a signal to the. So you'll have a control unit in the back of the vehicle. So it's not sending this CAN bus message to the bulb itself. Obviously, the bulb is just on or off. It doesn't have any computing power. But
no intelligence. Yeah.
You mentioned before, Chris, the node. So there'll be there's many CAN nodes. Each door has its own CAN node all around the place, and the message gets sent to that CAN node. It gets sent to all of the nodes, in fact. And the message is important. The message then will say, hey, the brake lights need to turn on, and then there'll be the circuit within that node that says, hey, that's me, or that's the message for the brake lights, turn it on.
Well, then I think we don't need that camera here anymore, right?
Oh, no.
Okay, because
then if the node will also pick up, if it's turned the brake lights on, it can also determine if there is no current going to that as well. So it can then say, hey, look, there must be the bulb is blown within the system. So that's most likely the case of what's going on there. So I think just to wrap up, we can have a look at some of the faults, what they look like. We've got the oscilloscope running nicely on CAN low speed, and there's something called ISO faults, Christian. That's the different faults that you have. There can only be, how many?
Basically, was around 8, something like that. Let's see. What will we have? We have basically, so CAN high can be short circuit obviously to ground or to plus. Same goes with CAN low. Then they can also be short circuit with each other, so that CAN high and CAN low goes together with each other. So where we now at 5. Then you can also have, of course, a resistor in the different wiring, which causes to have a smaller amplitude, for example. But the nice thing here is that we basically can activate these standard faults with the system. So you don't have to manipulate the car and make some funny stuff there and break it. You can just go on one of the fault simulation cases, and then here we go.
Exactly. So this, for example, I've just changed the time resolution to 5 volts per division now, because what we've done is a classic fault where it's connected, so the CAN low, so the red, is now connected to 12 volts. So before we were at 2 volts per division, we only have 2, 4, 6, 8. So we didn't see the 12 volts here, but that's now CAN low connected to the
which is basically at 0 volts.
And then we'll see over here, and this is again, so that all of a sudden the trigger is now out of range. So you've got to be really aware. Okay, how do I work here? What am I looking for? Don't just expect to see the same results over and over again. Here, for example, we're seeing now that the CAN high, the blue signal, is now short-circuited to ground. So it can't send the signal is being absorbed by the ground of the system, and it's not being sent around to the network, for example. You can see there's a little bit of residue coming through on some areas there, but the system is working fine.
And there you need the oscilloscope, so you can't see that now with the multimeter, because the nominal voltage of this would be 0 volt basically. So, and when this then is connected to ground, you don't see a difference on the multimeter, but you just see it on the oscilloscope as you see that there's no signal change anymore.
Go to another situation, you can see again the trigger is out of range. So the best thing is to do is start with the trigger off and just get a feeling of what's going on there. So here we can see most likely channel A. Okay, so set the trigger up, channel A, and now we have CAN low is now to ground, short-circuited to ground. Go through.
That would be something you can measure with a multimeter then, as this is normally at 5 volt and there it goes to ground then.
Exactly. And this one, we can actually see the two signals are short-circuited together. So that's that signal. I've just inverted channel A so that we can see it. Channel B, if we do this, wrong. I was going to say go back up to where it's meant to be, but obviously it's the same. That's the signal that I was talking about before in the police car with the screw going through the middle of the twisted wires.
Exactly. That you have linked, you've just connected physically both channels with each other.
This one here is also quite interesting. So this is showing that part of the CAN node is gone missing. Now this last piece, that's the acknowledge bit, is that correct?
That's true. Yeah, we have the CSC and then there's the acknowledge bit, which basically says, yeah, signal, not sent, but signal arrived, received, exactly, yeah.
And so it was unable to, it said, yeah, we've got the signal, but it wasn't able to send the signal on. So there was one of the nodes in the network is missing.
Absolutely, and that's funny that there you see some kind of interruption when you measure the signal on the one side. Maybe you measure on both channels the signal, and then you go to another measuring point where you just measure the acknowledge bit there. So there you know with CAN low speed that the signal arrived at the CAN node, and the CAN node then who got the signal wrote the acknowledge bit on the channel. And it will write the acknowledge bit on both channels as soon as it arrives the message. So, and then you see, when you just see the acknowledge bit, then you know that you're basically behind the interruption. So there is the interruption is already done, and you measured now behind the interruption where the CAN node who got the signal on the other channel just sent the acknowledge bit.
And this is now showing the same fault on the different, so the CAN low side. And this one here, to finish up, I think pretty obvious to see there's a high resistance on the CAN high signal as well.
That can easily be created to corroded connectors or whatever, something in that range basically. So you will find that at older cars obviously.
So I think that's a pretty good overview about what is CAN, what does it look like, even going into a little bit of diagnostics, just to understand it. Obviously going onto a vehicle is then another big step, but we obviously think it's important to understand what you're looking for when you start going into diagnosis. You know, you're using vehicles in the workshop or in the, in the college where you're starting to learn things like that. It's quite easy to destroy connectors, back probing or pulling the door panels off, things like that. So it's sometimes a good idea to get an idea of how the oscilloscope, you've seen how critical it was to have the right oscilloscope settings.
Absolutely.
So, if you don't have the right time frames, where's the trigger, where's it operating, if it's just out of range or not.
And that's also so important. I mean, here it's now easy because we have basically 2 CAN nodes and you can practice the correct measuring. But in the car, you can't do anything without a circuit diagram of the nodes. You need to know where are the nodes, and you need, it's like a town map which you need there, that you know where you are and where you measure, because without this you won't get any idea what's going on in the car. So just make sure when you're on the real car that you definitely have the circuit diagram of the canvas in your hands, that you, like I said, it's like a map, that you know where you are in the car right now and where you measure.
It's also worth noting as well, talking about when you go to the vehicle and trying to diagnose a problem. I know, for example, a lot of people say with Volkswagen, you just disconnect the node and you can see quite easily, does the oscilloscope change? You can see if that node or somewhere before or after that node is causing the problems. It's not every vehicle has that capability. There's something called termination resistors. There's resistors that are in the system that allow it to basically be in a loop. And they can sometimes be found within the control unit, sometimes they can be within the wiring harness. But what's important is if you just disconnect the control unit while it's awake, can actually destroy the control unit. Someone told me about, they did that on a vehicle and they had to buy a new control node for $1,000. So it's not always the best method. But really understanding oscilloscope is critical here.
So, and I think we're good. Let's call that a lesson. Let's call that a day. Basically, as we planned this video for 5 minutes. I'm pretty sure we're far above it. But there you see how much content it is just necessary to deliver in order to understand just the fundamentals here. And when you want to have more information on these basic systems, on this basic content as well, just leave us a message on YouTube, on LinkedIn, wherever you want, and we will have more deep dives into the basic content. So basically we're talking about hybrid and electric vehicles, but in order to understand the electric drive system as well, which is also using CAN bus, so you find CAN bus also in a high voltage battery communication, for example, it is important to understand what this is. And yeah, we're gonna stop here now. If you want to have more information about those topics, just leave us a comment here, write to us whatever you want. We are happy to do more on this. All right.
Thanks very much and have a good one.
Have a good one. Bye bye.
Happy diagnosis.